Hello everyone, my name is Chris Fitzpatrick, and welcome to my Physics 2212 Lab 5 presentation. The purpose and the physics fundamentals for this lab are to collect observational data of a magnet falling through a conductive tube of aluminum foil, to model the magnet/tube interaction computationally, and to compare the computational predictions with your observed data. And the physics fundamentals are magnetic field, force, and flux, and Faraday's law, Lenz's law, and Ohm's law. Here are the instructions for the lab. Here they are continued. Here at the bottom it says, it asks why can't we use a ferrous tube, and that's because it would interfere with the effects of Faraday's law, and it would make the results inaccurate. Here are the experiment results. So we've got the tube length is 0.31 meters, the tube width is 0.006 meters, the inner radius is 0.022 meters, and the outer radius is the width plus the inner radius, which is 0.28 meters. The magnet mass is 0.024 kilograms, and the dipole moment, which is what we got from lab 3, or what I got from lab 3, is 1.713 amps times meters squared. And here are the values for the trials, and the average time ended up being 1.272 seconds. And the results of the experiment were that the magnet falls slower than when just affected by gravity, the net force is less than when just under gravity's effect, and the tube created for the project causes an upward force to be induced on the magnet. Here are the parts of the code that I edited. Here's the first slide, and I added in all of my values. All of this was maintained the same. Added in my values down there, and my mu value of 1.713. I then added in the values for enter time and exit time, values for the def dipole B, as well as everything for def calculate, deflux, dt analytic, and then I added in fgrav and ring.current and fnet, and bar.vel and bar.PHYS, and that's it. This is the graph that I got using my mu value, and as you can see, it is not exactly to scale with how it should look, so I redid it with a mu value of 3, and this looks a lot more accurate as to what it should look like. And then interpreting the simulation, the intensity of the coloring ring on the tube indicates the magnitude of the current flowing through each string. Red and blue indicate current flowing in opposite directions. Which color corresponds to the clockwise current and which is counterclockwise? How can you know? And after observation, red is counterclockwise and blue is clockwise. And this combination slows the magnet down. And what happens to the dynamics of the system when you flip the magnet around? The results of the experiment would not change, but the current would flow in opposite directions. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? My model was somewhat inaccurate when using the mu value I received from lab 3, but was otherwise accurate. Split the tube in more rings, and check for any experimental or human error in the experiment. And what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The magnetic force increases, flattens out, or is equal to the gravitational force, and then decreases over the magnet's drop. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? And Ohm's law would cause the current to be very large, which would cause the magnet's air time to be even longer. And what if holes or slots were cut into the tube, and how would this affect the ring currents in your model? The model would have less rings than previously, which would cause the magnet to fall faster. And that concludes my presentation for Lab 5. Thank you very much for watching, and if you're interested in replicating this lab experiment, hopefully this provides good enough instructions, and I hope you have a great day. Bye.